So what about the node class? We have been discussing that this node class is going to be the building block for the disjoint set. And why is it good to have a disjoint set? Because with the help of the disjoint set, we are able to decide in constant time complexity or approximately constant time complexity whether there will be a cycle in the graph or not. And basically, this is crucial for Kruskal algorithm. So the node will have a private ID first, so a private integer ID. It's going to be a unique index for each node in the tree-like structure. Then, as we have discussed in the theoretical section, we are going to have a so-called rank. It is basically the approximate count of nodes below this given node. So basically, it is something like the depth of the tree. Then, it's going to have a reference to the parent node. That's what we have been discussing, that all the nodes is pointing to somewhere. It can point to the parent node or it can point to itself. If the given node parent is itself, it means that this is the root, so this is the representative of the given disjoint set. So I'm going to have the node constructor. In the node constructor, it's going to have a rank and it's going to have an ID and it's going to have a parent. And basically we just have to set the this.rank is equal to the rank, this.id is equal to the id, and this.parent is equal to the parent itself. Okay, and I'm going to generate getters and setters for all of them. So basically these classes are quite easy. There's nothing special about it in the sense that nothing complex. Okay, so basically we have an ID, we have a rank, basically the height of the tree, and a parent node. Okay, so what about the disjoint set? The disjoint set supports three operations as we have discussed: the make set, the union, and the find operations. I'm going to have some variables, so private integer node count is equal to 0. Okay, integers are initialized to be 0 by default, but whatever, just to make sure that it is clear. Okay, I set it to 0. Then I'm going to have a private integer set count. Basically, we would like to track that how many nodes do we have and how many disjoint sets do we have. Okay, 0 at the beginning, and I'm basically have a private list of nodes. These are the root nodes or the representatives. As you may recall, okay, what is a disjoint set? A disjoint set is going to contain distinct unique items. And if we find, so if we look for a given item, then it's going to return the representative, not the value we are looking for. Okay, so the disjoint set constructor is going to get a list of vertices. This list of vertices is going to be the vertices of the graph. Okay. Basically this dot root nodes is equal to a new array list, and we are going to have as many disjoint sets at the beginning as the number of vertices in the graph. So that's why it's going to have the vertices dot size. So what does it mean? That we would like to assign a distinct disjoint set, basically a node, to every vertex in the physical graph. Okay, and I'm going to have this make sets, and I'm going to specify the vertices. Okay, so what about this make sets? It's going to iterate through all the vertices, so for vertex v, for example, in the vertices list, and it's going to call another method, for example, make set on the v vertex. Okay, and this v vertex is basically going to create a new node. I'm going to call it n. I'm going to create with the rank 0. Then I will have the ID, the root nodes dot size is going to assign integers in ascending order 0, 1, 2, 3, 4 and so on. So the root nodes.size, and I'm going to have the parent as a null. And then I'm going to have the vertex. Okay, I'm going to rename it to vertex. The vertex.set node is going to be equal to this newly created node. Then I'm going to have this root nodes.add. I'm going to add this node to the root nodes. I'm going to increment the set counter, and I'm going to increment the node counter. Okay, so basically we assign a single node to all the vertices in the graph. So that's why we iterate through all the vertices in the graph and we make the distinct set. Okay, so we will have the find and the union as far as disjoint set is concerned. So I'm going to have this public integer find, and it's going to have a node as the parameter. And basically I'm just going to have a current node. It is equal to the n at the beginning, and we have to look for the root. Basically we are looking for the representative. So while the current node that get parent is not equal to null, we are going to have the current node is equal to the current node that get parent, because we are looking for the parent, and that's why the path compression is very good, because after the path compression the current node parent is its direct neighbor. So basically this while loop is not going to run very long, because the get parent is the representative always because of the path compression. So that's why it is a very good programming practice to do so. So okay, then I'm going to have the root node is equal to the current node. Then I'm going to have the current node is equal to the n again. And basically, I'm just going to have this path compression. So while the current node is not equal to the root node, I'm going to create a temporary node. I'm going to have the current node dot get parent, then the current node dot set parent is equal to the root node, and then I set the current node, and then I set the current node to be equal to the temporary node. So basically, we have been talking about the recursive implementation of the path compression in the theoretical section. This is the iterative form. Basically here we get a node and we find its parent, and if the parent of this is not a null, then we are going to look for its parent. So basically in an iterative manner. And basically we are looking for the root node. What's the root node? It is the representative. This is how disjoint set works. And first of all, I'm going to return the root node.getID. We are going to return the ID of the root node, and this is the path compression. It is basically writing the pointer up to the root node again, but make each node below a direct child of the root. This is the path compression itself. And this alters the tree such that future calls will reach the root more quickly. So basically this is how we boost up our algorithm, and this is why asymptotically the find operation is going to take ordo 1 time complexity very fast. What about the other operation, the union? It's going to be a public void union. It's going to have a node 1 and a node 2, so two nodes. And basically it's going to merge two nodes together, and the node basically can represent a whole disjoint set. So this is how we merge two distinct disjoint sets together. First I'm going to get the representative for both of them. So the index 1 is going to be the representative of node 1. I'm just going to find the representative or the root node ID for the node 1. I'm going to find the same for the node 2. So we have the index 1 as the first disjoint set representative and the index 2 as the second disjoint set representative. Of course, if the index 1 is equal to the index 2, it means that these two nodes are in the same set. We just return. We cannot merge them together because they are in the same disjoint sets by default. So there is no point in merging them, of course. I'm not sure whether it is clear or not, but if the representative for two nodes are the same, it means that they are in the same disjoint set. If it's not clear, then take a look at the theoretical section because we have been talking about it. Okay, then I'm going to get the root nodes of each set. It's going to run in constant time as well. So I'm going to have the root. So this dot root nodes dot get the index 1. Because basically this is just the ID. A find is going to return the root.getID. Maybe another implementation is okay. I implemented it that it's going to return the ID, and we are going to find the node itself. So the root node we have found with the help of this getIndex because we store it in a list. Okay, so we have the root 2 is equal to this. That root nodes, by the way, it runs in constant time complexity, so doesn't matter. It is a very, very fast algorithm. Index 2. Okay. And basically, here comes what we have been talking about, the so-called union by rank, that we attach the smaller tree to the root of the larger tree. And that's why we have to keep track of the rank. Basically, this is the depth of the tree. And if the rank is bigger, it means that this is the bigger tree. So we have to consider that we are going to attach the smaller tree with the smaller rank to the larger tree with the biggest rank integer. Okay, so basically, if the root 1 that get rank is smaller than the root 2 that get rank, it means that we have to merge these two disjoint sets in a way that we have to attach the root 1 to the root 2 and not vice versa. And basically in code it means that we set the parent of the root 1 to be equal to the root 2. It means that we attach the root 1 and this disjoint set to the root 2. Okay, else if the root 1 dot get parent is greater than the root 2 dot get parent, it means that basically we have to do a, not get parent, of course we have to get the rank. Sorry for that. Of course we have to get the rank. Then we have to do that root 2 dot set parent is equal to the root 1. And anyways it means that they are the same. So in this case, we are going to set the root 2 dot set parent. So we are going to attach the root 2 to the root 1. And basically, we have to set the rank. So set the rank to be equal to the root 1 dot get rank plus 1. So we have to increment the rank of the root 1. Okay. And basically we have to call this set count minus minus y because this is how we track the number of disjoint sets, this set count. And basically after merging two disjoint sets, of course, we have to decrement the number of disjoint sets because we have managed to merge two disjoint sets into a single one. So of course the number of disjoint sets has been decreasing. Okay, so basically what this make sets? This make set operation is going to attach a disjoint set to every vertex in the graph. This is how we are able to run our disjoint set or union find data structure algorithm. Then this find is going to make use of the path compression, And basically we have a node, and for the node we are going to return the representative's ID with the help of iteration instead of recursive method calls, which is get the parent as far as the parent is not null. Then the union is going to merge two disjoint sets together, and basically this is the union by rank principle, that we are going to attach the smaller tree to the largest one. Why is it good? Because our final tree is not going to be so unbalanced, and if the tree is not unbalanced, then the operations is going to run very fast. So basically this is how we implement a disjoint set. Thanks for watching.